So Euler buckling. And Euler buckling involves the column or any structural element that has compression, and the flexibility in the system is going to be from the element itself. The supports, the things that are holding it, are generally assumed to be more rigid, at least in our analysis, than the body itself. So the flexibility, the buckling will occur in the element itself, not from the supporting elements. And just like with rigid body, with rigid link buckling, the equilibrium configuration may become unstable before the material fails. Here, though, we're only going to have to derive the equation for the buckling load once, unlike with rigid link buckling when we have to derive it through free body diagram every time. Here, we're just going to have to do it once, and we'll have an equation that we can apply. So let's consider an element that has an axial load. Eventually, I'm going to end up turning that thing around the other way, but let's say we have an element pin rollered, and so E, I, and L are E and I are constants over a length L. And so the question is, might that element not be perfectly straight, may have some imperfections, and of course it would. So I'm going to draw the deflections very large here, as we do with our deflected shapes. And remember, in the transverse direction, we call that deflection V. And so let's draw a free body diagram of our pin rollered element. So there's the pin at the left end. There's the roller at the right end. There's the applied external load F. And so let's do a little equilibrium. Let's spin a moment over here. How about at the right end? So if we spin a moment at the right end, it's going to give us a real nice equation that tells us F2 equals 0. Now we'll take a look at what's going on inside the element. So we're going to take out the blue saw. We'll cut that thing. And a little bit of this picture deals with some answers I want to get out later. So focusing on, we've got an element that has some sort of transverse deformations in it. And so where I've cut it, we're sitting at a deflection negative V of x. V of x is going to be positive in the up and down direction. And at the cut, we've exposed the three internal forces. We've got the possibility of axial force, shear, and moment. Noticing that we've cut this thing at a distance x, so there's our dimension in the x direction. So in this free body diagram, we'll take a look at summing forces in the y direction, in the up-down direction. That's going to tell us that the internal shear is equal to 0. From this point, we're going to go ahead and apply equilibrium equation about the left end. We'll spin a moment, and we will end up with an equation with two terms in it. So we will have negative m of x. We'll also have a contribution from the internal axial force, and we've already found that that's equal to 0. So from the axial force, we will have a contribution in that direction and lever arm of minus v of x. So those two terms equal 0. So just a little bit of math. Actually, just multiplying through by negative, we get that the internal moment and the internal axial force are related to each other by the transverse deflection v of x. And so this equation, right, was derived by using a displaced configuration for the beam. So we also know that the internal moment divided by EI is equal to the second derivative of V. That's the second order beam equation. And shuffling that around, it would be the internal moment is equal to the curvature times EI. So we're going to go ahead and combine the equation that we've got up here. Call that equation 1. We'll combine that with equation 2, and we will end up with a equation that has EI times curvature minus P times V. And the way we derived that was where the internal force or the applied external load was causing tension. So for compression, we'd end up with a positive. And just sort of rewriting that, this is a second order differential equation for transverse deflection V. So it's a homogeneous differential equation. So we are going to find the solution. You could use eigenvalues. You can use method of lucky guess. But we're going to end up with sines and cosines. We're going to have harmonics and unknown coefficients A and B, modulating the sine and cosine terms. So we've got some boundary conditions that we're going to apply. So we know back in our picture, we knew that the transverse deflection at the left end, where the pin was equal to 0. Transverse deflection at the roller, which is at the right end, x equals L, was also equal to 0. So let's apply those. First one, we use V at 0 equals 0. So if we go ahead and plug in 0 for x, 0 for x, we would end up with a conclusion that A has to equal 0. Cosine of 0 would be 1. Sine of 0 is 0. So there's our first conclusion. So cosine term goes away. So there's our solution, our current solution after one application of a boundary condition. So we need to apply the other boundary condition at V of L equals 0. So we've got two possibilities. When we plug in right here, if we plug in an L for x, we've got two possibilities. One would be that B is equal to 0, and that will be actually known as the trivial solution. Or the other one would be that sine P over EI square root times L has to equal 0. So that would occur when the argument of the sine is equal to 0 plus or minus pi plus or minus 2 pi. And this starts getting into the issue of what the shape of the deflection is going to be at buckling. And so the theorem of minimum potential energy tells us that the mode of buckling will be in the least amount of strain energy. And so that means we're going to end up with a shape that had the least amount of curvature in it. That'll be where we settle our first equilibrium point. So as we kind of look at what happens here when 0, pi, 2 pi, the shape of this start to look like this. If it was 2 pi, it would look like that. We'd have more if it was 3 pi. And looking at that first shape, which was the pi, we end up with the least amount of curvature. Clearly this shape here has a lot more curvature, and if it's got more curvature, then it has more strain. So the shape that has the least amount of strain energy would be where the argument is equal to pi. So concluding that, we'll use that answer. There's the equation. I'm going to square both sides of it. Pi squared, L squared, radical disappears with P over EI. Solving this for P, we get an equation for the critical buckling load. Pi squared EI over L squared. Again, noting that this was completely derived for a pin-pin end conditions. So let's go take some inventory of our solution. So we've got that V of x is equal to B sine, and the argument is P over EI square root times x. So we're going to take this answer for P right there, we're going to plug it in right there into the equation. We'd end up with a little bit of cancellation with EI, and we'd end up with V of x is equal to B sine pi over L times x. So there's the picture that we've got. We've got a half sine wave going from x equals 0 to x equals L. So you kind of see a little bit more with the theorem of minimum potential energy as to the shape that we've encountered here with our buckling load. So let's explore our equation for V of x just a little bit more mathematically. If we take the derivative, we'd end up with a cosine, right, that would come out by chain rule. We'd end up with doing another derivative. We'd end up with an expression for curvature. And the reason why we've done this is we wanted to highlight what we've actually found are moments of, or locations of zero moment, because we know the curvature is proportional to the moment in the beam equation. So the moment would be equal to 0 when x equals 0, and also when x equals L. And we're going to use that for non-pinned end conditions here in just a second. So the equation actually is going to be rewritten as P critical is equal to pi squared EI over LE, the effective length of the column. And that effective length is going to be based on boundary conditions, and that's going to come down to finding the distance between the points of zero moment on the beam with the boundary conditions given. So we've got 3 additional boundary conditions combinations to look at. So we'll do these one at a time. So we've done pinned. We're going to do fixed pinned, fixed, and then fixed free. So let's go back up here. And so we're going to draw the deflected shape for the buckling that would occur. So we've got over here at the right end at the pin, we have a point of known deflection. Right? The rotation is free to occur. At the fixed end, we have both zero deflection and zero slope. So what we need to do is connect these 2 points. And so there would be a lot of different options about how to do this. So one way to do this from a deflected shape point of view would be that curve right there. And so this curve, however, is going to violate the theorem of minimum potential energy. You see all the curvature that's there. We obey the boundary conditions, but if we just draw this a little smoother, we would have a picture that kind of looks like that. Now, that being said, it could be up. It could be really high up. We don't know the magnitude. That has to do with the coefficient B, but we do have some information about the points of zero moment. So we would know that at a pin, the internal moment equals 0. And we have another position of zero moment because we've got a curvature change. We have an unhappy to a happy beam. So roughly right about there would be a point of zero moment. So although this beam has length L, it actually has an effective length, or distance between points of zero moment, of 0.7 L. And so we'll do this 2 more times. We'll do it with a fixed beam, so with a buckled load. And so both end conditions have zero deflection and zero slope. So connecting them with the most smooth line would look something like that. Points of zero moment, roughly where does the curvature change? We've got unhappy beam going to happy beam, and then back to unhappy. So somewhere about those points we would have zero moment, and the distance between those is going to be 0.5 L. So these factors are going to be on your equation sheet as well. So last one would be fixed free. So this would be our 4th one. So down here we've got fixity, so zero deflection, zero slope. Up top we've actually got quite a bit of freedom. So we've got a picture that looks like that. And so I'll draw it even better. There would be the load F. So we have to get a little creative here about what point of zero moment. We realize out here we'd have zero moment. And so looking at the other end of the beam, what about here? And well, just thinking of this as a free body diagram, that's actually where the moment would be as big as anything. That would be the largest on the beam in total. So I've got to get a little creative on this one. I'm going to redraw it right here. We need just a little more room. There would be the free end, so we have to kind of project this onto the other side. The point of zero moment would be all the way over there. So for a fixed free, the effective length is actually twice the actual length. So from a stiffness perspective, and kind of go back and look at this top one here, we've got a beam that has, as compared to the pinned roller, we've got something that has increased kinematic restraint. So we have something that will have a higher buckling load. Remember that P critical is going to be pi squared EI over LE squared. So as that number goes down, the critical buckling load goes up. So let's look at something that was fixed. So again, increasing the kinematic restraint, we end up with something that has an even smaller effective length. Right, the most flexible of all would be the fixed free. So we've got a fixity down here, we have complete kinematic freedom at the top, and so turns out that the effective length is equal to twice the actual length. So of all three of these, the one on the bottom, the fixed free, would have the smallest critical buckling load. So P critical, pi squared EI over effective length squared. If we define the critical stress from the calculation of P over A, if we divide each side by A, we'd have sigma critical. There's the addition of A. There's a special cross-sectional term, right, due to the geometry of the cross-section of the elements called the radius of gyration. You can think of this as the resistance to buckling. So I over A right there is defined as the radius of gyration squared. So the radius of gyration is just the square root of I over A. So the larger the value of I over A, the larger the critical stress, the buckling stress is for the element. So if we then rewrite that, it looks a little funny, but we then have the radius of gyration in the denominator, and so it would be LE divided by the radius of gyration squared. And so this is called the slenderness ratio. So that term is actually what governs the calculation of the critical stress. And so there'll be a class of problems where we want the buckling stress and the yield stress to be exactly the same. We want those to occur at the same time. That would be the optimal use of the cross-section and the material. So there'll be a class of problems where we set those two equal to each other and then solve the problem. So if we plot this, if we plot the stress versus the slenderness ratio, we would have a curve for sigma critical and a couple of different classifications here. When sigma critical is less than sigma yield, right, where the yield stress is going to be constant throughout, then the column is considered slender. That would mean that the column is going to buckle before it yields. So the stress value, sigma critical, would govern. At some point, we end up with equality between yield and sigma critical. And when sigma yield is less than sigma critical, we end up with a short column. So that would be something that would yield before it buckles. So to wrap this up in a summary of the buckling, again with the axes, so let's take a look at an element here. I'll put X along the longitudinal direction of the element, Y and Z in the cross section. And so critical buckling load, pi squared EI over LE squared. And so with an element that is rectangular or non-symmetric, we can end up with the possibility that the moment of inertia about the Y and the Z axis may not be the same. Right? That'd be a function of the cross-section. Also, the effective lengths for buckling about the Y or the Z may not be the same. We could have different boundary conditions And so the result would be that the critical buckling load for the y and the z axis may not be equal to each other. So buckling about the y axis, right, would require movement of the element in the xz plane. Buckling about the z-axis would be movement of the element in the yx plane. So if we kind of draw that here, if we were looking for buckling about the z, we would have movement in that direction. Right. Buckling about the z would be movement in the yx plane. Right. Buckling about the y-axis would be movement in the zx plane. So depending on how the problem is laid out for us, we may need to check buckling about the two axes in the cross-section of the member.